Hello, welcome to Higher Edu Tutor. Today we will learn about the work of a force, and the outline of today's lecture will be the following. So we'll learn about what is a work, and how do we calculate it? And how about the case of several particles or a system of particles? And how do we calculate the work done by all forces applied on a system of particles? So let's go ahead and start. So let's consider a particle that is subjected to force F. The particle is at this position and at this time. Due to the applied force, the particle will move along a path. So this is the path defined by S. So let's consider first that the particle has moved due to the force F a baby distance to the position or the new position P prime. So we have here, let's say, the origin of my reference. So from the origin we have the position of the particle when it is at position P, let's call it R, and the new position R prime defines the position of the particle when it is at position P prime. So due to the applied force F, the particle will move a distance or a baby distance dr. So that dr is R prime minus R. The magnitude of this dr is ds. Now we can define the work done by the force. It's actually a baby work done by the force F to move the particle from position P to position P prime, so that it moves a baby distance ds. So the baby work is equal to the dot product of the force vector times dr. Now if we assume that the angle between the force F and dr is theta, then we can evaluate the dot product as the magnitude of the force F times the magnitude of dr, which is ds, times cosine the angle theta. Okay? Now if we consider that due to the force F, the particle, let's say, moved from one position to another. So let's say we are interested in the position at this time, let's call it position 1, and another position somewhere here, position 2. Then the work done by the force F to bring the particle from position 1 to position 2 is U12 is equal to the integral between R1 or position 1 to position 2 of F dot dr. So if we evaluate this integral, we get the integral between S1 to S2 of f cosine theta ds. Now if you look at this integral, you see that we have the integral of the function f cosine theta with respect to s. So this means that if I have f cosine theta as a function of s, like this, then the work done will be the area under the graph between S1 and S2. So this area is simply the work done by the force F to bring the particle from position 1 to position 2. So there is a particular case of f cosine theta being constant. So f cosine theta, if it is constant, then the work done by the force F to bring the particle from position 1 to position 2 will be f cosine theta times the integral of ds, of course, between S1 and S2. Then this gives me f cosine theta times delta S. So let's set up now the equation for the work done by the weight. So imagine we have a particle and it has a weight W. So imagine that this particle moves from position 1 to another position. So let's say this is the path followed by the particle, and the particle moves from this position, let's say position 1, to another position, let's call it position 2. Initially, the particle had a position R1. Particle has a position vector R2. So, if you remember, the work done by any force to bring a particle from position 1 to position 2 is the integral of f dot dr. Now, this is between R1 and R2. Now, the force F in our case here is only the weight, and it is equal to minus W, the magnitude of the weight, which is mg times k. Now, dr is simply R2 minus R1. So we have R1 can be expressed in terms of the Cartesian coordinate system. So we have three components: x1 I plus y1 j plus z1 k. Similarly, R2 is equal to x2i plus y2j plus z2k, so that dr will be equal to x2 minus x1, let's call it dx I, y2 minus y1 will be dy j plus dz k, and dz is z2 minus z1. Now there is a trick here, and students should be aware about it, is that the calculation of the work done by the weight I don't recommend generally to apply this formula to calculate the work done by the weight because often students they get tricked with the negative sign. So to facilitate the calculation of the weight, I usually advise my students to look at the problem and always see whether the weight is doing positive or negative work, and based on that they put the positive or negative sign in front of the expression W delta Z. So I generally recommend them to use this formula instead. So I ask them to calculate the weight, the work done by the weight, using mg times the height being the distance, the vertical distance between the position 1 and position 2 of consideration. Then they can put positive or negative in front of the expression based on whether the weight is doing positive work or negative work. Now the weight is doing positive work or negative work, it all depends on the dynamics of the system itself. So imagine you have a particle like this, and it is an one incline, and you don't apply any force on the particle, and you expect the particle to go down. If you expect the particle to go down, then due to the weight, the particle will go down regardless whether you apply force, external force or not. Then in this case the weight will be doing positive work because your intention is to have the particle to go down the incline. So in this case we can put here small sign here to show that it is what doing positive work. Now imagine the other case when you apply an external force, and that external force is intended to push the particle upward, then in this case you expect that the weight will not do a positive work. A positive work. So you expect the particle to do what? To expect the weight to do a negative work. Okay, you expect the weight to do a negative work. Now this is very important because this shows that you understand the dynamics of the system and you know which force will be doing positive work and which force will do negative work. So let's consider now another case which I find really interesting and explains very well the choice of the sign in front of the work done by the weight. Now imagine there is someone who is on the bottom of the building and expecting somebody to send a ball, and that person is on the top of a building. So the person on top of the building won't throw the ball. He will be just letting the ball go down on its own weight. So we have the ball going down with the weight, right? So in this case, the work done by the weight will be positive. The weight times what? The height. And this will be the height. Okay? Now, we don't expect the guy on top of the building to throw the ball because he will be just applying an extra force, and that force will do an extra weight that is useless. Unless the person is trying to apply another force to decrease the time required for the ball to reach the guy at the bottom of the building. Now, if we consider the case where the guy at the bottom of the building is trying to send another ball to the guy on top of the building, then we don't expect that guy, we don't expect the guy at the bottom of the building to just hold the ball and expect the ball to go on its own upward. This doesn't sound logical, right? Why? Because we expect that the weight will do what? A negative work that must be countered using another work. So we expect the guy at the bottom of the building who is trying to send this ball to apply another force F. Okay, to apply another force F, and that force F will do a work, and that work must be greater than the work done by this weight. In this case, and only in this case, will the ball go upward to the guy on top of the building. Okay, now let's summarize. If the weight is helping, then the work done will be positive. And if the weight is not helping, then the work done by the weight will be negative. These are the two cases that we have. Okay. And this works for any kind of force, as long as you understand the dynamics of the system. So let's now try to calculate the work done by spring force. So imagine we have a spring, and this spring has a length L. So let's consider this is the position 1 of the spring. And when you apply force to a spring, you stretched up till this position. Let's call it S2. So this is the force you applied. When you apply the force F, there will be a force that is mobilized in the spring, and that force, let's call it Fs. That force appears only when you try to change the original length of the spring, and it will be always opposite to the direction of the external applied force. Now if we try to calculate the work done by the spring force, let's call it UFS, it will be equal to the integral Fs times dr. Now Fs and dr can be evaluated based on the axis, positive axis we are going to choose. So let's say this is my positive s-axis. In this case, we will have Fs equals minus the magnitude of Fs times I, and dr will be equal to, now dr direction, since you are stretching this direction of F, so this will be the direction of dr. So dr will be dsi, positive dsi. Now we can evaluate now the integral, so UFS will be equal to minus Fs times ds, because this dot product I times I is 1 between S1 and S2. Now we can put the negative sign outside the integral between S1 and S2. We know that Fs, the spring force, is simply K times S, and S the amount of stretch or compression. So you can put here K times S, then ds. And this shall give me what? What is the integral of S ds? Is S squared over 2. So minus half K times S squared, then the integral between S1 and S2. Finally, we can put here the work done by the spring force will be equal to minus half times K times S2 squared minus S1 squared, which is very important. Now let's talk about the principle of work and energy and how to derive it and how to apply it in later lessons. So imagine a particle that is moving along, say, this path. And the particle is subjected to different kinds of forces. So maybe we have one force here, another force here, and another force here, and so on. Now, all in all, the particle, say, is moving in this direction, and this is the velocity tangent to the path. And assume that we are going to consider the case when the particle is moved by these forces from this position until this position. Now, if you take the resultant of all these forces, you find the force, say, in this direction. So this will be the resultant force. This is the resultant force. Now, not all the components of this force will contribute to the work done, right? So not all of them will do work. If you recall, we have the work done by any force to bring a particle from one position to the other position will be equal to the force times the distance traveled times cosine the angle between the direction of motion and the force. So this is the force applied. Let's say this is the direction of motion, okay? And this is the angle between them. So only the component of the displacement in the same direction of the force that we are going to consider. That's why we multiply by the cosine, the angle between them. Okay? Now, imagine we have here the resultant force now. I drew here the tangential axis and the normal axis. So this is the tangential axis and this is the normal axis. I showed here the velocity direction, and we have here the position 1 of interest, and this is the position 2 of interest. And the particle is subjected to the resultant of the forces applied on the particle originally. Now, not all, as I said, not all the components of the resultant force will contribute. So, if a force that is subjected to a particle and makes an angle of 90 degrees with the direction of motion, that force will not do any work. Cosine the angle 90 degrees equal to 0. So we only consider the forces that are not perpendicular. In this case, if we resolve the sum of all forces, the resultant will resolve it into normal and tangential components. We find out that these forces are the components, the normal component. So sum of the forces in the normal direction will not do any work, okay? Will not do any work, okay? Doing no work. And only the components in the direction of the motion or the direction of the velocity will contribute to the work done. So only these forces. So we have here the sum of forces in the tangential direction. Only these forces will contribute and will do work. Yeah, will do work. These forces, the normal forces, will not do work because simply they are in the direction that is perpendicular to the velocity, which is the direction of motion. So cosine 90 degrees is equal to 0. Good. Now we will calculate the work done by this force, the tangential force, and see how it is related to the energy. So first, using the equation of motion, we have sum of the forces in the tangential direction is equal to the mass times tangential acceleration. Okay? Now, if you recall, we have V is equal to ds over dt. So the velocity is simply the derivative of the position with respect to time, and the tangential acceleration is the derivative of the velocity with respect to time. If you divide v by at or the inverse, what you get? You get at is equal to v dv over ds. Now if we take this and substitute here, what you get? You get sum of the forces in the direction of t, or direction of motion, is equal to the mass times v dv over ds. Now you cross multiply and you get sum of the forces in the t direction times ds is equal to m times v dv. Good? Now what we do, we integrate, okay? We integrate both sides of the equation. So we integrate from here between S1 and S2, and we integrate the other side of the equation, the right hand side of the equation. We can put the mass m outside the integral, and we have here the integral of v dv between v1 and v2. Okay? S1 and S2 is our positions of the particle at position 1, and S2 position 2. We have here velocity v1 here, and we have here velocity v2. Clear? Good. Now let's evaluate this integral. Now if you look here, we have the integral of f ds. This is very easy for us. We know that it represents what? Work done by the tangential forces, by all tangential forces, to bring the particle from position 1 to position 2. Now we can put the mass here. Now what is the integral of v dv? We know that the integral of x dx is half x squared. So we can put here half. Now v squared and between v1 and v2. And this gives me half the mass times v2 squared minus v1 squared. So this is the principle of the work and energy. So let's look at this equation. We have the total work done by the forces applied on the particle is equal to half m times v2 squared minus v1 squared. So this will be equal to half m v2 squared minus half m v1 squared. And if you recall, this represents what? The kinetic energy. And this also represents the kinetic energy. So is equal to T2 minus T1. All in all, we have arrived at the principle of work energy that relates to the work done by all forces to the energies. So is equal to T2 minus T1. So this principle states that the work done by all forces is equal to the change in the kinetic energy. So the work done by all forces is equal to the change in the kinetic energy. Okay. This is very important principle, and we can apply it in any situation. I mean, for any dynamical system, regardless of the type of forces that are applied on the particle. So we have seen that for one particle, the principle of work energy states that the total work done by all forces is equal to the change in the kinetic energy between position 1 and position 2. Now that we have this, imagine the case where you have not only one particle, but you have a system of particles. So in this case, you have different masses that are subjected to different forces. And in this case, so let's say this is the path followed by the system. The total work done by all forces is very simple, and the principle can be written as follows. So the total work done by all forces is equal to the sum of all kinetic energies at position 2 minus the sum of all kinetic energies at position 1. So it is the same as we have stated for one particle, except that we are going to use the total kinetic energy and at position 2 minus the total kinetic energy at position 1.